now we are looking at Briggs section 3.5, still talking about derivatives. Okay, so we'll specifically in this section talk about derivatives of trigonometric functions. All right, so before we start with that, let's look at these two limits that we're just going to define. So we've got the limit as x approaches 0 of sine x over x. Okay, and that's going to be equal to 1. And we can see that if we look at this graph of sine x over x, okay, as x approaches 0 from either side, okay, your function is equal to and is approaching 1. Okay, we also have the limit of cosine minus 1 divided by cosine of x, cosine of x minus 1 divided by x. And that the limit of that as x approaches 0 is going to be equal to 0. Okay, if we look at the graph of that function, okay, as x approaches 0, okay, your function is equal to 0. All right, so those are going to be two limits that's going to be important as we move, because we can then use those to evaluate other limits, such as these. Okay, so as long as we've got whatever's inside the sign, as long as that's the same as the denominator, then that is going to equal 1. Okay, your limit as x approaches 0. Okay, because that was our definition up here. Okay, so as long as whatever's in here is equal to whatever's on the denominator, then that's equal to 1. Okay, so sometimes it'll be obvious. Sometimes it won't quite be so obvious, but we can make it so it's that way. So what does the argument in the sign have that this denominator doesn't have? Well, a 4. So I can multiply by 4 over 4. Okay, and I get the limit as x approaches 0 of 4 times sine of 4x divided by 4x. Okay, and I can pull that 4 out front because it's just a constant. Okay, and so then we know that the limit of this, we know that that's equal to 1. So since that's equal to 1, then we just have 4 times 1. Okay, so just 4. All right, and then sometimes you might have to, so in this case, we've got a 3h here inside, and we've got a 5 out here. All right, so we need to somehow make this numerator a 3h. So we can multiply by 3 over 5 over 3 over 5. All right, and so that gives us a limit as h approaches 0 of 3h over 3/5 sine of 3h. Okay, which will be equal to 1 over 3/5 and then times 1. So just 5/3. Okay. And the other identity we have up here works the same way. Okay. So if you can put it in this form, then you know that limit will equal 0. All right. So we've also got here, it's given to us, our argument's equal to what's down here. So that'll be equal to 1. So it doesn't matter if something's added or subtracted, as long as the argument is equal to either the denominator or if it's flipped the numerator. All right. And then we've got the limit as x approaches 0 of tangent of 2x over x. Now, your first instinct may be to do this exactly like we did the other ones, but you have to remember, this is not a tangent. This is not a sine function. It's a tangent. So what we have to do is rewrite this, okay? So we can rewrite it. So tangent's the same as sine over cosine. Okay? So tangent's the same as sine over cosine, so we can rewrite this as the limit as x approaches 0 of sine of 2x over cosine of 2x times 1 over x. Okay. And then we can split this again, and we get the limit of, as x approaches 0, of sine of 2x over x times cosine of 2x. Okay, so I can multiply by 2 over 2 to make these equal. Sorry, that should be 1 over cosine of 2x. All right, and so now I get 2 times the limit of sine of 2x over 2x times 1 over cosine 2x. All right, so we get the limit, or we get just 2 times this limit is equal to 1. Okay, and then this limit is also equal to 1. Okay, because we can just plug 0 in for our x, and so we get 1 over cosine of 0, which is 1, so just 1. All right, so our final answer for that one is 2. Okay. So if you get like a tangent or something, you can always split it up. All right. And then with this last one of this type, we end up with a sine over sine. Now, remember, these signs cannot cancel. Okay? Burn that in your brains. Signs cannot cancel like that. They are an argument, not a value in this case. All right? So what we can do, though, is to split it up. So the limit as x approaches 0 of sine of 7x times 1 over sine of 5x okay, and then I can multiply the whole thing by x over x, because think, we need an x for a numerator for this piece, we need an x for a denominator of this piece. And so x over x is just going to be 1. So I can multiply by that and then rewrite my limit. That's a 0. So we get sine over 7x over x times x over sine 5x. Okay, so then we can multiply by 5/7 over 5/7. Okay, and we get the limit as x approaches 0 of 1/5 times sine of 7x divided by 7x over sine of 5x divided by 5x. Okay, so we get 1/57, or sorry, let's do it this way. This 1/5 is just going to be 7/5 times this piece is 1, this piece is 1, so just times 1. So our answer is just 7/5. Alright, so those aren't so bad. We just have to put them in the correct form that we know how to do. Okay, so then we can look at derivatives of sine and cosine. Alright, so your derivative of sine is going to be cosine. Straightforward. Your derivative of cosine is going to be negative sine. Okay, so remember, derivative of sine is going to be cosine, but to go backwards, it's negative. It's one way to think about it. Okay, and I've got the derivation here, but if we do the derivative of sine and we use our limit definition of the derivative, okay, and do some algebra, it cancels down to where it's cosine. Okay, and we did the same thing for cosine here. You're not going to be asked to reproduce this, but here so you know where it's coming from. All right, and we can do this graphically. So if we've got the derivative we've got just sine, and if I were to take and draw my derivative graph, that would give me the cosine graph. Okay, but if I were to start with the cosine graph and draw my slope graph of it, that would give me the negative sine graph. Okay, so that's another way you can kind of visualize it. But just remember, so derivative of sine is cosine, but the derivative of cosine is negative sine. Okay. All right, and so we can use those to evaluate the derivatives of some following functions here. All right, so this first one we'll have to use the product rule on because we're dividing. So we'll say that m prime is equal to, remember it's low d high minus high d low. Okay, so the original bottom times the derivative of the numerator, so the derivative of cosine, which is going to be negative sine, okay, minus the original top times the derivative of the denominator, so the derivative of sine will be cosine, over the denominator squared. Alright, and so we can rewrite that as negative sine squared x plus cosine squared x over sine squared x. So because this times this negative, so that term would be negative, and this term is negative, so we can factor that negative out. And so then that gives us this identity. So we know that sine squared plus cosine squared is equal to 1. So that allows us to simplify this, so it's negative 1 over sine squared. Which, if you remember your trig functions, this is the same as the negative of cosecant squared. Okay. So with sine and cosine, or trig functions, you're using the same derivative formulas that we were talking about the last couple sections. Okay? The same formulas. You're just now applying them to trig functions. Okay, so for instance, this one, well, we know what is sine squared plus cosine squared? That's equal to 1. So my derivative of my function n, so n prime is going to be 0. Okay? Because it's a constant. Now, without simplification, okay, we could do it without simplification, but you would end up having to use the product rule twice, which would not be fun. It would still get you down to the derivative being 0, but doing the product rule twice is just not going to be fun. So we recognize that identity and simplify our lives a little bit. Okay. And then we can also do with L here. So we've got a logarithmic function times the trig function. Totally cool. We have to do the product rule. Okay. And I think I misspoke earlier and called something the product rule when it was really the quotient. But if you're dividing, it's quotient rule. If you're multiplying, it's product rule. All right, so if we're looking for L prime, okay, again, use the product rule. So we have EX times the derivative of cosine, which is negative sine of X, plus derivative of e to the x, which is just e to the x, times cosine of x. Okay, and we can, if we want to, simplify it a little bit by factoring this x out and writing it as cosine of x minus sine of x. But there's really not any other way to factor or to simplify that one. All right. Okay, so there was 3 more examples. That's how we can use those same derivative rules. Okay. We can also, here this says find the derivative of our function y, and it specifies that we need to simplify. Okay. So we can take our derivative, and so we'll have to use the quotient rule. Okay, so that'll be y prime is equal to 1 plus sine x times the derivative of our numerator minus the original numerator times the derivative of the denominator. So derivative of 1 is 0. So then the derivative of sine is just cosine of x. Okay, divided by 1 plus sine of x squared. All right, so then we can take and rewrite it. So the only thing we'll really have to do in this case is this derivative, which we'll have to use the product rule for. And then we can just rewrite this as a cosine squared. So we can do all that. So we end up with 1 plus sine of x times our product rule here. So derivative of x is just 1 times cosine of x plus x times the derivative of cosine, which is just negative sine of x. Okay, minus x cosine squared of x. All that divided by 1 plus sine squared of x. Or sorry, 1 plus sine of x squared. You cannot distribute the other piece in. Okay. All right, so then we can then distribute this 1 plus sine squared times this cosine, or 1 plus sine times cosine plus x times this negative sine x. Okay, and so that is equal to cosine of x minus x sine of x plus cosine of x sine of x minus x times sine squared of x minus x cosine squared of x all divided by 1 plus sine of x squared. Okay, so all I did was multiply these two pieces, which gives me all of these terms, just like you would if you were multiplying like a plus b times c plus d. Okay, same FOIL. Alright, and then we see we've got an x times sine squared minus an x times cosine squared, so we can factor out a negative x, and that'll knock that down to 1. Okay, so if I factor that out, I get cosine of x minus x times sine of x plus cosine x times sine of x minus x times sine squared of x plus cosine squared of x. All of that still divided by the same. Okay, so if we're looking at it, we took these two terms and factored out this negative x, and what that does is that leaves us with this sine squared plus cosine squared, which we know is equal to 1. Okay. So then I can regroup my terms. So if I regroup them a little bit, so I've got, let's do cosine of x plus cosine x times sine of x minus x sine of x Okay, all I did was take that 1 to 1, and then I took and I regrouped these pieces. Okay, now when I'm looking at it, I can say, okay, well, if I can get a 1 plus sine term in both of these, okay, then I can factor it out and cancel. And what do you know? I've got a cosine in both of these, so I can factor that out. So that becomes cosine of x times 1 plus sine x. Okay, and then we'll use green. I've got a negative x and a negative x that I can factor out. And that leaves me with a 1 plus sine of x. And then it's still divided by okay, and now we can see where I've got a 1 plus sine x in both of these, so I can factor that out. It's times cosine of x minus x. All right, and so then I can cancel this with one of these, it's on the bottom, and I'm left with cosine of x minus x over 1 plus sine of x. Okay. Which is as simple as it will get. Okay, so what we did with that is we took the derivative. Okay, our derivative had been taken completely at this piece, at this step. So then beyond that, it was just simplification. Okay, because we knew something had to cancel because the directions had specified to simplify. Okay, and anytime it specifies simplify and you've got something, a fraction like this, look for something to cancel with the denominator. Okay, so because I knew I needed to simplify and I was looking for this 1 plus sine term, then I could find it in each of my two pieces to my equation up top. Okay. Alright, so then we've kind of just got, it's listed as a theorem, but it's just a kind of a summary of your trigonometric function derivatives. Alright, so we've got our derivative of sine is cosine. Derivative of cosine is negative sine. Alright, we talked about those. You should also know that the derivative of tangent is secant squared. And the derivative of cotangent is negative secant squared. Okay, and then that the derivative of secant is secant times tangent. And the derivative of cosecant is negative cosecant times cotangent. Okay, and these are all, 6 of these are some things you should have memorized. I think when I had to memorize these back in undergrad, I kind of used this table and found a pattern that worked for me. So I would look at it and find something that works for you so that way you've got them memorized. Okay, and so we'll use these for a couple of examples. So if we look here, we've got y is our function here. We wanted to find y prime. All right, so we'll rewrite it. So we'll rewrite this first term, so it's 4 times x to the minus 1 minus 9/13 tangent of x. All right, and so we want to take, well, that's just rewriting y. That's not the prime yet. So now we can take our derivative, though, and we'll use the power rule for this first part. So it becomes negative 4 over x squared. Right, and then the second part is minus 9/13 because that's just a constant. And then we know that the derivative of tangent is secant squared. Okay, so there is our y prime. All right, and a lot of times your derivatives will be a combination of rules like that. We can also do this secant theta over 1 plus secant theta. All right, so we've got a quotient rule here. Okay, so that's our first step. So we're looking for g prime of theta. And so we'll have the original denominator times the derivative of the numerator. And we know the derivative of secant theta is going to be secant theta times tangent theta. And I am going to run out of room. Look at that. Here, let's move this over. There we go. All right. All right, so then minus secant theta times the derivative of the denominator. Derivative of 1 is a constant, so that'll be 0. And then we'll take the derivative of secant again, which we know will be secant theta tangent theta. Okay. And then all of that divided by 1 plus secant theta squared. Okay. And so I won't take you through the algebra, but if we multiply both of these out, Okay, then it cancels down with the subtractions to, oops, that's not a pen, secant theta times tangent theta divided by 1 plus secant theta squared. Okay, so I would suggest you can distribute these, okay, and make sure you know how they cancel. But it should work out just fine and not be any issues. All right. So if I scoot that one over so we can do this last one of these example types. All right. So we've got the derivative of 3 things that are being multiplied together. So we'll do the product rule, and in this case what you do is, so with the original product rule, okay, you take the derivative of the first and leave the second alone, and then swap where you leave the first alone, take the derivative of the second. In this case, you're going to have 3 terms that you're adding together, and you'll take the derivatives one at a time, leaving the other 2 alone. Okay, so here we can color code this real quick. All right, so our first term is going to be the derivative of the first term, so dd theta of theta squared, and then we leave the other terms alone. So sine of theta times tangent of theta. All right, and so then it's that plus the original first times the derivative of the second term. Oh, I was going to leave this. Okay. And leave the third term. And then we take and leave the first 2 terms. Take the derivative of the third. Okay, so anytime you've got something that's multiple terms or more than 2 terms like that, it's just step by step. You take the derivative of the first term, leave the other ones alone. Take the derivative of the second term, leave the other 2 alone. Derivative of a third. You just make sure you take the derivative of each one like that. Okay? And so now we can actually do our derivatives and see how it simplifies. So we get 2 theta, sine of theta, tan of theta, plus, and then in this case we're taking the derivative of the sine of theta, so that was cosine of theta, times tan of theta. And then in this case we're taking the derivative of the tangent of theta, which we know is secant squared of theta. Okay, and then we leave that. Okay, I guess I had room enough to write it out going like this, but you see what's happening. Okay, so there's derivatives, and of course there'll be more derivative examples on the extra examples. I suggest you work through those. Just 2 other ways that you might see these problems. You might be asked something like this if we've got our function f, and we want to find a that would make f continuous. Okay, so just like when we did this before, you do the limit as x approaches 0, because that's our piece here, of whatever your function is. So in this case, 3 times sine x over x. So then we take this limit, so bring the 3 out, and then this limit as x approaches 0 of sine x over x, which we know is 1. So our limit here is just 3. Okay, so that tells us that a should be equal to 3, and that would make f continuous. Okay. So you might see something like that, and it's just like we were doing before when we were looking for what value would make that continuous. All that's different is that there's a trig function in there now. All right, and then lastly, I've got two limits. Yeah, lastly, I've got two limits here. So remember that there's a limit definition of your derivative. Okay, and so we can use that, okay, to evaluate limits. All right, so we know that we've got the limit as x approaches pi over 4 of tan of x minus 1 over x minus pi over 4. Okay, we also know that tangent of x is equal to, we know that tangent of pi over 4 is equal to 1. So we can rewrite this as the limit as x approaches pi over 4 is equal to the tan of x minus tan of pi over 4, because that's equal to 1, divided by x minus pi over 4. Okay, and so what we've done is we've put this in the form of our limit definition of our derivative. Okay? So we know that this is equal to the derivative with respect to x of tan x evaluated at x equals pi over 4, which we know is secant squared of x evaluated at x equals pi over 4, which we know that's the same as 1 over cosine squared of pi over 4, which is equal to 1 over root 2 over 2 squared, which is just 2. Okay, so you can use the fact or the relationship between our limits and our derivatives, okay, so that limit definition of the derivative, and we can use that to evaluate limits using our derivatives. Okay, so another way we could do that is if we're looking at this. Okay, we know that sine of pi over, we know that sine of pi over 6 is equal to 1/2. Okay, so I can rewrite this. So we've got the limit as h approaches 0 of sine of pi over 6 plus h minus sine pi over 6, okay, divided by h. And so then that is our form of our limit definition of a derivative. So we know that then our function is sine of x. So it's the derivative with respect to x of sine of x evaluated at x equals pi over 6, which we know is just cosine of x evaluated at x equals pi over 6. Okay, which we know from our unit circle is root 3 over 2. Okay, so instead of being given the function and saying, use the limit definition to find your derivative, okay, they're giving you the limit definition, and you have to recognize what the function is and then calculate the derivative to find your limit. Okay, so it's moving backwards, but still the same thing. All right, so that is all for the lecture video for 3.5. There will be extra examples posted, and I suggest you try those out. And if you've got issues, you can come to office hours or ask questions in our discussion board. All right, I will talk to you next video.